Alrighty. Welcome to the last section of Chapter 5. Yes, that is exactly what the section is. It is Section 12.1, Synthetic Division. We're still in Chapter 5, absolutely, but I find that the synthetic division goes very, very well with the long division. So this will be our second time talking about division. And so you can think of this as Section 12.1, aka Section 5.6. In your book, it talks about a lot of other things first, but since it fits so well, I just decided to move it up. However, we're going to talk about a lot more than just synthetic division today, because synthetic division, for those of you who know what it is, you remember, hopefully, that it is very, very easy, very, very straightforward, and it does not take a lot of time. So we're going to talk a little bit more about the other parts of division as well, stuff like the division algorithm, the remainder theorem, the zeros of a polynomial. We'll go into all of that, as well as synthetic division. And then that'll kind of close out all of our operations on polynomials. If you remember, we've got addition and subtraction, we've got composition, multiplication, and now we're finishing up division. But let's start with the division algorithm. The division algorithm sounds super complicated, but it's not. It basically is the same algorithm you've been using this entire time to solve via long division. Yeah? It just relates all of those pieces we were discussing last time. So we were discussing how when you have a division problem, you take a dividend, some function f of x, and you divide it by some divisor, g of x, right? So whether you're dividing 6x minus 4 plus, 6x squared minus 4x plus 3 divided by 2x plus 5, that would be your dividend divided by your divisor, right? So your dividend would be what's on top, your divisor would be what's on bottom. After you finish up the problem, you end up with a quotient, right? That's your answer. Q will be the quotient. And sometimes, not often, most of the time though, you end up with a remainder. R will be the remainder. So you end up with a quotient and a remainder. Now if we were to write all these pieces in the long division form we were working with last time, it would look something like this. So we'll go up here. We had our dividend that was underneath the long division sign, right? Our divisor would be on the outside. Our quotient would be chilling up here in the answer, right? And then you'd see the remainder in kind of two places. You would find it down here, right, at the very end, but then you would kind of drag and drop it to be a plus remainder up here, right? Plus the remainder over divisor up here. And that's kind of what it would look like when you break it down in long division form. However, I agree with you that that's a little confusing to look at, right? Without colors, that's not very helpful. They both say div and all that jazz. So there's another way we can relate these. We can relate them in sort of this equation right here. Now, don't panic. I know it's got 4 different functions in it, but it's nothing that you guys can't handle. It's just relating back all 4 of your pieces. So we've got that the dividend is equal to the divisor times the quotient, and if you have one, you add a remainder. So that's just those 4 pieces over again, right? And let's look at what that means. Well, last time when we were talking about remainders, we discussed the example of 6 divided by 5, right? And it doesn't go in evenly, so we have a remainder, right? So 6 divided by 5, just remind ourselves over here real fast with not green. 6 divided by 5 is equal to 1 with a remainder of 1, right? 1 with a remainder of 1. Okay, so now let's take a look at those pieces. 6 was our dividend, right? The thing that was being divided. And that was equal to our divisor, which was 5, times our answer, which was our quotient, which was 1, right? And then we also had that remainder of 1 to add on. A remainder of 1, right? Yes. Awesome. Now, we have our division algorithm. This is how it's set up. When we set it up this way, we note that we also get a true statement. When you divide something by 5, right, divide the 6 by 5, if you wanted to get back to 6, you multiply it by your answer, and then add your remainder. And that's what they've done here. They said, okay, that whole dividend is equal to the divisor times the quotient plus the remainder. In other words, 6 is equal to 5 times 1 plus 1, or 5 plus 1, which is 6, right? And that's basically what they're saying, the division algorithm. that is how it works for numbers. It works exactly the same as if it does for what am I talking about? Polynomials. So it works for numbers, it works with polynomials. Let's take a look at an example we did before. We've got our same setup here for the division algorithm. Dividend is equal to the divisor times the quotient plus the remainder, right? And using the colors for me helps really spell this out. The dividend is the divisor times the quotient plus the remainder. Now yesterday, or for a couple of you guys last time, we did a problem with this huge dividend, right? 6x to the fourth plus 9x cubed plus 2x squared minus 8x plus 7, right? We took that polynomial and we divided it by 3x squared minus 2. And I believe it was actually an r. I think it was 3r squared minus 2. You can go back, we'll check out that problem. Let's see, where was it? It was right here, right? 6r to the fourth times 9r cubed plus 2r squared minus 7r plus 7 divided by this guy. And we had that whole missing term, and so we ended up having to plug it in, and we found out it was this as an answer. So we got this as a quotient and a remainder, right? Remainder was up the top here. Remainder over the divisor. Now, when we want to take that and plug it back in the division algorithm, we said our dividend was this. We divided it by that. What we got as an answer, our quotient is here, and our remainder is there. So don't think you're coming up with this whole new convoluted whole bunch of equations. You're just taking in the different parts of a problem you've already done, right? It just says that if we wanted to go back, we would multiply the pink and the blue, or the pink and the purple, add the red, and we would get the blue, right? That's all it says. So that's basically what the division algorithm says. It says that if you divide something by a divisor and you get a quotient and you add the remainder, then you can get back to your dividend, and this basically shows you how all these pieces work together. Alright, cool. So the division algorithm can be put together for either long division or what we're about to learn now, synthetic division. Synthetic division, as the name implies, is exactly like long division, only you're doing it in a sort of synthetic format. You're taking out a bunch of stuff, so you're sort of synthesizing what's happening in long division, but it's much easier because you don't have any coefficients. So let's take a look at that. We've seen problems like this before, right, where we have we've got this whole polynomial being divided by this divisor. We end up with this dividend right here, and it looks like there was a remainder of 80, which they didn't tack on yet. Now, what a synthetic division does is it takes out all of the x's. It takes out x's and x squareds and anything that's repeated at all. So it takes out anything variable-wise, and then it takes out anything that's even once repeated, and then it takes out any spaces, and it takes out any unnecessary things. So, or unnecessary numbers. Basically, it squishes long division down into something much easier and more manageable. Now, the only bummer part about synthetic division is that it only works for very, very specific divisors. Very specific divisors. These divisors have to be of the form, x minus k. And k there is a number. K there is a number. So k is a constant. And I know the constant doesn't start with k, but we use c a lot, so we're going to use k instead. So it's a number, x minus a number, right? So in our problem we had up here, the divisor was x minus 3, and that's why this worked. If you don't have an x minus 3, then you get into issues of subtraction, you get into issues of factors, things like that. So it has to be in the form x minus k. Now be careful, because if you see stuff like x plus 2, you might think that's not of the form x minus k, right? But you'd be wrong. X plus 2 is the same thing as x minus negative 2. So the k is just hidden in there as a negative number. That's totally legal. So that is actually of the form x minus k. So this could be x plus something or x minus something. Both of those will work for synthetic division. Alrighty, let's take a look down here. What we're going to do is we're going to divide 5x squared plus 16x plus 15 by x plus 2. And we just talked about how that x plus 2 is still of the form x minus k, so we can do this. We definitely can. This way, we've realized that, hopefully you realize by now, that k is equal to negative 2. So what we're going to do So we're going to set up a long division thing like we usually do. We're going to put -2 over here. We're going to put our k over there. K over there. And then just like in a matrix, we're going to take out all of the coefficients. So essentially, it's very much like a matrix where the idea is you drop away all the coefficients. Don't worry, we're not going to go into row ops with synthetic division. But the idea is we're going to drop away all of the x's. So we got 5 as a coefficient, 16 as a coefficient, and 15 as a constant. So we'll just kind of drag and drop those guys down there. All right, and then we're going to play a little game. And here's how the game goes. We are going to drop the first number. I like to say drop it like it's hot. And we're going to drop it down here. And then we're going to multiply. So -2 times 5 gives me -10. Oops, 10. So we multiply, drop, multiply, and now we're going to add. -16 plus -10 is it's +6. +6. Then we'll repeat. 6 times -2 is -12. And we'll add 15 plus -12 is +3. And we end up with these 3 numbers. And those 3 numbers end up winning the game. So that's our game. Our game, synthetic division, goes drop the first number. Second is to multiply. And the third is to add. And you repeat that over and over and over again until you run out of numbers to play the game with. The fourth step in this game is to finally put the variables right back in. So replace the variables. And that's kind of the fourth step that doesn't really go with the game, but it's like the fourth thing you need to do for the problem. Now, in order to put the variables back in, I want to make sure I put them in an order that starts building from the right. And I know this sounds a little confusing, but basically I want to make sure I get the right variables in there. I don't want to start with squared, right, because that's where the other one started, and I definitely didn't end up with a squared. I want to start with one less than that. What I like to do, though, is I like to actually start from the right-hand side and build to the left. The right-hand side shows me my remainder. This is my remainder right here. That's my 3 as a remainder. So over here, I have the remainder over the divisor. That divisor was x plus 2. X minus k, or x plus 2, right? After that, I move 1 to the right, and that's going to be my constant. So plus a 6 as my constant. I move 1 more, and that's going to be my x power. So I'm going from the remainder to constant to x. If I had another one, I'd go up to x squared. If I had another one, I'd go up to x cubed. If I had another one, I'd go up to x4. Right, but I'm moving to the left, from the right to the left, and I'm adding an x for every time we go over. That's how you put the variables back in. And we end up with our solution. Our quotient of 5x plus 6 plus 3 over x plus 2. Awesome. It's so much faster than long division, which is amazing, but it only works for the form x minus k. Let's try another one. Very similar. I'm going to let you guys try this out. See if you can play that game. First, set up what is your k. That goes on the left-hand side. To play the game with the coefficients, and then see if you can plug it back into plugging the variables. See if you can plug the variables back in to get a quotient. Alrighty, I hope you had some time to try this out all by yourself. If not, then I hope you know what you're doing. K here is equal to -3, right? Just like up here, k was equal to -2 because it's minus k. Here, k is equal to -3. So I'll go stick -3 over here on the side, and I'll pull out all my coefficients. I have a 1, a -4, and a -21. And then I will play the game. So start by dropping it like it's hot. 1 times -3 gives me a -3. Add those together. -4 plus -3 is -7. -7 times -3 is +21. -21 plus 21 is a 0. And I've run out of numbers, so the game is done. The last part is to put the variables back in. It looks like I have no remainder. 0 remainder. So my constant starts off with a -7. and then I add an x, 1x, right? So it looks like my quotient is x minus 7. Hopefully you got the same thing. Now just to prove to you that this is in fact just a synthetic version of long division, I'm going to go ahead and do long division over here as well. So I'm going to do x plus 3 divided 2 x squared minus 4x minus 21. Was it minus 21? Yeah. Alright. I'm going to do this kind of fast because we did long division last time and I don't want to take a whole bunch of time talking about this, but I'll try to keep it at an appropriate pace. How many times does x go into x squared? That would be x times, right? X times x, x squared, x times 3, plus 3x. Now I'll subtract the 2. I end up with these two canceling. Negative 4x minus 3x is a negative 7x. And I drag this guy down. Negative 21. How do I get an x to a negative 7x? I multiply by a negative 7. Negative 7 times x is negative 7x. Negative 7 times positive 3 is a negative 21, and I subtract the 2 to get a 0. And I end up with the same answer. And if you look closely, not only do I end up with the same answer, I've got a lot of the same stuff going on here, right? I've got, okay, drag 1x down, make 1x, right? I've got negative 4 plus negative 3. In other words, I've got 4 minus 3, right? Negative 4 minus 3. I end up getting negative 7 or negative 7. Multiply that by the 3. You end up getting the 21, right? So you drag the 21 down. Adding those together, they cancel out. Adding those together, they cancel out. So this is really just a synthetic version. The blue is just a synthetic version of what's happening in the pink here. That's why it works. All right. If you have any questions about that, go ahead and pause. Otherwise, we're going to go on to the next problem. But just like with long division, this one has a little bit of a problem. First off, it's not in the k, right? It's not in the x minus k. This is definitely x minus k, where k is equal to 2, right? It's x minus k, so it's not negative 2, right? We always kind of take the opposite. K is equal to 2, so I've got a 2 over here. But the problem here is I've got a missing term. Just like in long division, that's an issue here. The game doesn't work, right? So instead I should have 5, 4, 3, 2, 1, x, and then the constant of 50. I don't. So I'm going to have to put in a 0x here. So same thing goes here, same fix. Negative 4, 1, 6, 2, and then now I have to put in a 0 to account for that x, that missing x, and then 50. Alright, now I can play my game. That's a lot more numbers, but it doesn't really matter. Works for however many numbers you have. Alright, first one I drop it like it's hot. Multiply negative 4 times 2 gives me a negative 8. Negative 8 plus 1 is a negative 7. Negative 7 times 2 is a negative 14. And I'm just multiplying and adding as I go across, multiplying and adding. 6 plus negative 14 is negative 8. Negative 8 times 2 is negative 16. Plus 2 is negative 14. Times 2 is negative 28. Plus 0 is negative 28. Times 2 is negative 56. And add to 50 gives me a remainder of 6. Alright, the numbers got a little bigger, but that's okay. The game was played, right? The game was played. I figured it out. Now I'll put the variables back in. Starting with that remainder. Let's do it down here. Negative 6 over x minus 2. Right, I always got to put the remainder over the divisor. And then that, next up is my constant, negative 28. Next up I'll add an x, minus 14x. I'll add 2 x's. Oh, and actually I've run out of room, so I'm going to go up here. Negative 8x squared. Negative 7x cubed. I went up 1. And negative 4x to the 4th. So I end up with the polynomial. I know it kind of got cut in half for room, but negative 4x to the 4th minus 7x to the 3rd minus 8x squared minus 14x minus 28 minus the remainder of negative 6 over x minus 2. That whole thing is my quotient. Would have had the same answer in long division, but notice it took us like half the time. So that's very useful, right? Alrighty, let's do one more just to really hammer it out. Yeah. So I've still got the form x minus k, right? X minus k, so k here is equal to 4. Let's not do green again, let's do orange. K here is equal to 4, so I'll put the 4 over here. And let's see, I'll double check that I don't have any missing powers. 4, 3, 2, 1, 0. Nope, I'm good there. So it looks like my coefficients will be 1, 6, 9, 3, and negative 3. And I'm going to show you something that can happen with synthetic and long division. It actually happens with both. But let's see what happens. So I've got 4 times, first we drop it like I saw it, right? So we drop this 1 down. 1 times 4 is 4. 6 plus 4 is 10. 10 times 4 is 40. 40 plus 9 is 49. So notice, even though these numbers are getting bigger, I'm just going multiply, add, multiply, add, multiply, add, over and over and over again. 49 times 4, I believe it is 196. It is, in fact, it is 196. Add 3 to it, you get 199. Well, times 199 by 4, we get 796. And subtract 3 to it, you get 793. So my numbers got a lot bigger here, right? 793, 199, but that happens sometimes. It just happens. When you divide things out with the subtraction and the adding and the multiplication and all that jazz, sometimes you need 199 as a coefficient. All right, so we end up with a remainder of 793. 793. So we'll write that down as 793 over x minus 4 plus constant of 199 plus 49x's plus 10x squared plus x cubed. And we are finished. We just added an x every single time. Alrighty, fantastic. If you have any questions on how synthetic division works, make sure you pause the video now and get some questions answered, right? But we are going to go on to something called the remainder theorem, and it has to deal with synthetic division, though. It has to deal with synthetic division, so make sure you get your questions answered before we move on. Okay, so the remainder theorem. The remainder theorem, as you might have guessed, is all about the remainder. It's about that remainder, right? So that remainder we see, that 793 at the end of synthetic division. And here's what it says. It says, the remainder theorem says, if you have a function, f of x, right? So some function that you know that is being divided by something of the form x minus k. So something like this up here. Something like this, where you have a function, x to the 4th plus 6x to the 3rd plus 9x squared plus 3x minus 3, divided by something of the form x minus k, right, x minus 4 being an example. Then when you divide that out and you get a remainder, that remainder will be the same thing as if you had plugged in k. So that's the idea here. In other words, let's say you were, so like in other words in our problem here, 793 would have been the same answer as if we had plugged in k equal to 4. So if we had plugged in 4 to all of this, we would have also gotten 793. That's what the remainder theorem says. So let's see if that is in fact true. Let's see if it's true. We're going to first divide this f of x function using synthetic division, and then we're going to actually plug it in. We're going to do it both ways, and we're going to make sure we get the same answer. So here f of x is equal to 2x cubed minus 5x squared minus 3x plus 11, right? And it goes 3, 2, 1, 0, so I don't need to worry about filling in any things when it comes to synthetic division. And k here is equal to just negative 2. I don't need to switch it. K is just part, just k in the form of the remainder theorem. So I've got k is equal to negative 2. Let's go ahead and divide that synthetically. So you've got negative 2 on the outside, you've got a 2, a negative 5, a negative 3, and an 11. And we'll play the game. First we drop it like it's hot. So we got 2. 2 times negative 2 is negative 4. Negative 5 plus negative 4 is negative 9. Negative 9 times negative 2 is a positive 18. 18 plus a negative 3, or negative 3 plus an 18, is a 15. 15 times 2 is negative 30. And negative 30 plus 11 is negative 19. Alright, so we got negative 19 as our remainder. Now what it should say, the remainder theorem should say that when we plug in negative 2, we should also get negative 19, but let's double check that. Let's double check that. We always want to make sure what they're saying is true, right? So let's do this like we did in the last couple sections, f of negative 2, right? So let's just plug in negative 2. So we've got f of negative 2 is equal to 2 times negative 2 cubed plus 5 times negative 2 squared minus 5 times negative 2 squared. That would have been an issue. Minus 3 times negative 2 plus 11. Plus 11. Okay, let's simplify that out a bit. I'll start with those exponents. 2 times, let's see, negative 2 cubed would be a negative 8. Minus 5 times negative 2 squared would be a positive 4. Minus 3 times negative 2 plus 11. Now I'll do some multiplication. I've got negative 16 minus 20. Negative times a negative is going to be a positive 6 plus 11. And last but not least, I can do the addition and subtraction. So I've got negative 36 plus 6 plus 11. Negative 36 plus this would be negative 30 plus 11. And that indeed does end up being negative 19. So it is true. Our remainder ended up matching our function, or our evaluated function. Sweet. That's what the remainder theorem says. So each one of these should end up being the same. Therefore, if it's much easier to just plug in, or it's much easier to synthetically divide, one or the other, you can know that you'll get the same answer either way. All right. The last thing we're going to talk about today, and the last thing in Chapter 5, is using synthetic zeros to determine if something is a zero of a polynomial. What that means is, you've guessed it, a zero of a polynomial, that means is the remainder 0. Is the remainder, whoops. We'll say, is the remainder 0? Is the remainder 0? That's the question. That's a zero of a polynomial. Now there's a whole bunch of things that also go with the zero of polynomials. If you remember from secondary 2, this is where things would cross the x-axis. That's what makes them a zero of a polynomial. So if you had something like a quadratic, then the zeros would be right here and right here. A way to check if something is a zero is to use synthetic division, and it builds right off the remainder theorem, because if this is equal to 0, this is equal to 0, the y is equal to 0, right? Then f of x is equal to 0. In other words, f of k is equal to 0. And just as we saw in the last one, if you want to evaluate a number, you can use synthetic division. So this is just kind of a piggyback off of the remainder theorem. We're just testing to see if the remainder is maybe not another number, some number, but if it is in fact 0. That's what we're checking here. Alright, so use synthetic division to check if the values of k are zeros. In other words, check if they are equal to 0. So let's start with a here. I have the k, negative 5, and I have this function f of x equals 2 x to the 4th plus 12x cubed plus 6x squared minus 5x plus 75. Quite a long function, right? But synthetic division should help us figure out if we don't want to do negative 5 to the 4th, we can maybe just synthetically divide and see if it actually ends up being 0. So let's do that. I've got 4, 3, 2, 1, 0, so I don't need to worry about numbers, but about filling in. 2, 12, 6, -5, and 75 are my coefficients. I want to check if this number is actually a 0, so I'm not going to change it or anything. It's not like it's x minus k. I'm just going to put in k there. And we're going to divide it. Alright, so drop it like it's hot. 2 times -5 is -10. 12 minus 10 is 2. Or in other words, 12 plus -10 is 2. 2 times -5 is -10. 6 plus -10, -4. -4 times -5 is a positive 20. 20 minus 5, that would be a 15. 15 times -5, that's going to be a -75. -75 plus 75 is a 0. Alright, what can we conclude? Now that we have these 5 numbers, what do we conclude about this -5? Yes, it is a 0 of the polynomial, right? It is a 0 because this remainder, by the remainder theorem, f of k is equal to 0. And if f of k is equal to 0, then we know it is a 0 of the polynomial. So this would be a big fat yes. Awesome. Try out this other one over here. Use synthetic division to see if that is a 0 of that polynomial. And if it is, say yes. If it isn't, say no. And then we'll do it together in just a sec. Okay, so I hope you paused the video. I hope you had a chance to try this out on your own. I hope you noticed something as well. There's an issue here. There's a missing power. What power is missing? That's right, x to the third is missing. X to the third is missing. I hope that you're actually answering me when I'm talking, when I ask you a question, like what power is missing. That's right. I know it sounds a little silly if you're not actually answering me, but you know, that's just the price we pay with videos. Alright, so x to the fourth, there's a missing x to the third, and then x squared, and then x, and then 1. So when we synthetically divide this, we need to put in that x cubed, right? So we've got a coefficient of 1, and then a coefficient of 0, and then a coefficient of 1, -3, and 1. So watch out for that. But the k, we just put down k, right? -4, just like we would any other problem, but it's not in the form of x minus k, so we don't need to worry about switching anything. Drop the 1 down. 1 times -4 is -4. -4 plus 0 is -4. -4 times -4 is positive 16. Plus 1 is 17. 17 times -4 is -60. Plus -3 is -63. 63 times -63 times -4 is a positive 252, and then you add that to 1, you get 253. So what can we conclude about this number, this k? That's right, I hope we can conclude together as a class that this is not a 0 of the polynomial, right? This is not a 0 because the remainder does not equal 0. And therefore, by the remainder theorem, if the remainder is not equal to 0, f of k does not equal 0. And if f of k does not equal 0, this is not a 0. So this would be a big old no. Alrighty. We've talked a lot today about different things. We've talked about the division algorithm, how that works together, how synthetic division works. It's just a mimic of long division. We've talked about the remainder theorem and the zeros and how those two piggyback each other. We've also talked a lot this chapter about the other operations, addition, subtraction, composite, multiplication, and division, all of which will be on your test. Use the time now to begin your homework or ask any questions you think you have about either this section or any of the other sections so that we can tackle our test coming up soon.